Okay, so the next topic, okay, so would be about conservation of momentum. Okay, so if we have two bodies, no, so which collides, so the sum of the momentum before the collision, no, so is equal to the sum of the momentum after the collision. So that is the conservation. That means the momentum before the impact, no? So the sum of the momentum before impact is the same, no, as with the sum of the momentum after the impact. Okay, so we have here, no, so the conservation of momentum formula. So you have there the momentum. Okay, so take note, momentum is the product of mass and velocity. So V1 and V2 denotes the velocity, no? So before the impact, and of course you have the V1 prime and V2 prime denotes the velocity after the impact. Okay, and then we have the term coefficient of restitution. Okay, so denoted by the variable E. Okay, so mathematically that is the negative ratio between the relative velocities. No? So after impact over to that of the relative velocity before impact. So which means, or relative velocity means the difference, no? So that is negative ratio. So you have here the formula, okay, and then we have here, no, the condition for coefficient of restitution. So that is equal to 0, okay. So 0 when the two bodies, no, so stick together. That means after the collision, so the two bodies, no, so move as one. Okay, and then you have there 1. Okay, so 1 for the coefficient of restitution if it conserves, no, so the kinetic energy after the collision. Okay, so for perfectly elastic bodies. So So basically, just remember in elastic bodies, so you have the 0, and then for perfectly elastic bodies, so you have the 1. Okay, so otherwise it will be given, no, so in the problem. Okay, so we'll try to use, no, so the concept of conservation of momentum. Okay, for problems number 4 and number 5. Okay, so let us dwell now so number 4 and number 5. Okay, so okay, so for example number 4, so you have there two perfectly elastic balls, no? So take note that's elastic, so which means the coefficient of restitution is 1. Okay, so each of the ball, no, so weighs 6 pounds and 4 pounds, no? So they approach each other with a speed of 20 feet per second and 35 feet per second respectively. So what will be the speed of the 6-pound ball after they collide? So kindly uh, get, no, so the data first before we shift the screen to whiteboard. Okay, so okay, so for example number 4, so you have there as given. Okay, so you have there two perfectly elastic balls, no? So you have there the 6-pound ball, so it travels, no, in this direction. So that is V1, and the given weight, no, that's 6 pounds, and then also you have the other ball, so which travels in the opposite direction. So shall we say the speed is V2, and the weight is given to be 4 pounds. Okay. Now after they collide, okay, so uh, the ball okay, the balls collide, no, after. Okay. So making their direction, no, be reversed. Okay. So this would be V1 prime, and of course this would be V2 prime. Okay. So we use, no, so the concept of conservation of momentum, that is the sum of the momentum before. So the momentum before would be uh, M1 V1 plus M2 V2. Okay, so M1, that is 6 pounds, and V1 would be, of course, V1 plus, so that is 4 pounds, and then since V2 is traveling, no, to the left, so that is negative V2. Okay, so that is equal to the sum of momentum after. Okay, so the mass remains, no, the same. So you have their, of course, no, so you have their M1 V1 prime plus M2 V2 prime. Okay, so take note, V1 prime and V2 prime are the uh, speed, no, of the balls after the collision. Okay, so you have the 6, and since V1 is, take a look at V1, no, so that's negative V1 prime, course plus 4 times, so V2 prime. So that will remain positive because it is traveling to the right. Okay, so uh, okay, so we can, okay, so we can substitute the given. So that is 6 times V1 is said to be 20 feet per second, no? So that's 20 plus 4 times V2 is negative 35, so that is negative 6 V1 prime plus 4. Okay, so which gives us so we have here negative 20, that is equivalent to 6 V1 prime plus 4 V2 prime. Okay, so this would be equation number 1. Okay, and since it is given in the problem, no, that the okay, so it's given as two perfectly elastic, no, so that means the coefficient of restitution is 1. So that is E, so that is negative of V1 prime minus V2 prime. Okay, so divided by V1 minus V2. Okay, so this will be equivalent to 1, no? So this would be V1 minus V2. So that is equivalent to negative V1 prime plus V2 prime. Okay, so V1, that is 20 minus negative 35. Okay, so that is equivalent to negative V1 prime plus, okay, so you have there 20 plus 35. Okay, so we have here 55. So that is equivalent to negative V1 prime plus, so this would be equation number 2. Okay, so solving for the two equations, no? So you can use directly your calculators. So you have there, okay, negative 6, then 4, and negative 20. So you have the negative 1, 1, and of course 55. Okay. So, okay, so this should be, okay, let me check. No? So, okay, so I think we got the wrong sign here because V1 prime is negative, no? So this time. So this makes it positive. No? So negative of, so this would be negative of negative v1 prime. Okay, so this makes it positive here. Okay, so that would be, this would be v1 prime. Okay, so upon calculation, okay, so we have their, okay, so kindly go over with your calculators. So you have 1 and 55. So we can have v1 prime, that is 24, and v2 prime, of course, that's 31. Okay. So since we are asked to calculate for the velocity of the, or the speed, no, of the 6-pound ball, so the answer must be v1 prime. No? So this would be the answer. Okay, so that's 24 feet per second. Okay, so 24 feet per second. Okay, so now we go to, no, so the next sample problem. Okay, so okay, for item number 5, so you have there a 1,200 kilograms car that is moving east sa 30 meters per second, and it collides, no, so with a 3,600 kilogram truck, so which moves at a speed of 20 meters per second in a direction, so take note, so that's in a direction 60 degrees north of east. Okay, so the vehicles interlock and move off together, so which means that after the collision, so the two vehicles stuck, no, so with each other. So we are asked to calculate for the common velocity. Okay, so the common velocity. So we will be, or our approach, no? So the problem would be for inelastic bodies, no? Because the two stuck together, no? So when they collide. Okay, so that is for number 5. Okay, so we can have perhaps no, an imaginary axis. Okay, so vehicle A, so starting from this point, it moves to the east. Okay, so at a velocity of 30 meters per second. Okay, so this is 30 meters per second. Okay, so whereas another vehicle, okay, so stated in the problem, so another vehicle, so moving 20 meters per second in a direction 60 degrees north of east. Okay, so that is 60 degrees north of east. So assuming that this track, no, so starts from here, so it moves in this direction and they collide after. So since the two stuck together, so the two vehicles, no, so became one object and they travel at a velocity v. So, but initially the truck, no, so is traveling 20 meters per second. No? So to take note, 60 degrees north of east, so of east. So we make this one as our reference, and then this would be north, and then 60 degrees north of east. So that means the angle here is 60 degrees. Okay? So we need to calculate for the common velocity of the two. Okay, so we begin by writing the conservation of momentum. No, so okay, so that is m. Okay, so that's m1 plus m2 multiplied by v. Okay, so now as you can see, so the two vehicles, no, particularly the truck, no, so it's not in line, no, so with the motion or the direction of the car, no. So uh, okay, so what we do is for situations like this one, wherein the two objects, no, so though they collide, but they have different directions, so we do it first, no, so like we apply so conservation of momentum. Okay, so of momentum. So we do it first along x-axis. Okay, so therefore uh, okay, so therefore we break down, no? So okay, so we break down the components, no, for the truck. Okay, so this should be okay. So velocity of the truck along x-axis, and also this would be velocity of the truck along the y-axis. Okay, so along x-axis, so we apply m1 v1 along x plus m2 v2 along x, that is equal to m1 plus m2, and then the x component, no, of the final velocity of the two objects, no. So you have there 1,200 and 3,600. So this would be 1,200. So multiplied by v1x, no. So that is 30. So you can see, no. So the velocity or the direction of A is along the x-axis, no, plus 3,600. So the component of V2x, no? So that is, okay, so this would be V2y and V2x. Okay, so this would be, okay, V2x, that is, if this is 20, okay, so this would be V2x, V2y, 60 degrees, and this would be 20. So V2x would be this one, no? So V2x, that would be 20 cosine of 60. That is equivalent to M1 plus M2, that's 4,800 multiplied by the x component, no, of the velocity after the collision. So you can solve for Vx right away. So you have there Vx, that is equal to, okay, so this would be 15. Okay, so, and we also apply no, the same thing. So apply conservation of momentum force along y-axis this time. Okay, so you have the M1 V1y plus M2 V2y. Okay, so that's M1 plus M2 Vy. Okay, so the y component of M1 is 0 because it is traveling along, no? So the x-axis, so we can cancel this one out. Okay, and then you have the M2, that's 3,600. And V2y here, that's 20 sine of 60. So that's equivalent to 4,800 Vy. So finally, calculating for Vy, okay, so that makes it 13. Okay, so such that the velocity, no? So we can calculate velocity as square root of Vx square plus Vy square. Okay, so such that V, okay, so if we substitute these values, no? So we have there, okay, plus 15 square, and then you take the square root of it, so that's 19.84, or basically 19 point, okay, so that's 19.85. Of course, the unit of which is meters per second. Okay, so if the problem, no, so if the problem involves collision, no, so with different directions, so we need to solve the x and y components, no? So like the example presented to us, okay, or like in the example presented to us. Okay, so now we go to then, so the next topic, okay, so which is about, okay, so the next topic would be about work and energy, okay, so we define, no? So we define work as the product of the variable force multiplied by the distance, okay? And you have to take note that the force here is not just as simple as a force, okay? So the condition is that the force, okay? So the force, okay, so if this is the distance traveled, so the force, okay, so in this equation is the force parallel, okay, so take note, it's the force parallel to the distance traversed, okay. So if we remember, if we consider the force which is perpendicular to the distance, then that is what we so-called as moment, no? So that is not equivalent to work, but it's moment or torque, okay. So you have to take note, okay, so that the force that needs to be considered in the calculation of work must be equal to the product of the force, okay, or the product of the parallel force, okay, or the force, no, so which is parallel to the distance multiplied by the distance traversed, okay. And these are the standard units, no, for work. So we have the joule, erg, foot-pound. Okay? So and then the corresponding units also for the quantities force and distance. Okay? So then we define energy, no? So as the capacity to do work. Okay? So when you say energy, so since that is the capacity to do work, Okay, so okay, so that is okay, so that's energy, no? So the capacity to do work. Okay, and then we will be defining, no? So uh, the following, no? So energy, no? So we have the potential energy, and of course the what we so call the kinetic, no? Kinetic energy. Okay, so later on, we will try to explore the idea of the conservation of energy, no? And then we'll try to elaborate further. So how can we, no? So how energy is being conserved, and then also included, no? So in the discussion today, the okay, so that is the power calculation, okay, and then we have the law on conservation of energy, this one, and then might as well the relationship between work, no, and energy. Okay, so one by one we'll be taking them down. Okay, so for potential energy, so this is the energy possessed by an object by virtue of its height, no, or position relative to ground. So potential energy, that's equivalent to the weight multiplied by the height. Okay, so and then we have the kinetic energy, no? So the kinetic energy, of course, is this energy possessed by an object by virtue of its motion. Okay, so far, I think you have uh, this formula in your mind. Okay, so kinetic energy, which is equivalent to 1/2 mv squared. Okay, so this formula is for linear kinetic energy. Now that means the body is just running, no, in a plane. However, there is still another type, no, of kinetic energy which is given by the rotational kinetic energy, no, because sometimes as the body moves, at the same time the body also rotates, no, so that is why we have the rotational kinetic energy, no. So okay, and then we will explore later how we can equate the two. Okay, so for now we will be uh, going to encounter the following sample problems, no. So that is number 6, 7, and 8. Okay, so okay, so you have there in example number 6, no. So kindly take note of the given. Okay, so you have there a 40-pound stone is carried up a ramp. Okay, so along a path making a 30 degrees angle to the horizontal. Okay, okay, so the stone is carried, no, so in a ramp. Okay, so to the top of the building 100 feet high. Okay, so how much work is done? Okay, so okay, so this is for example number okay, this is number 6. So you have there, okay, so as per the problem, so you have there a ramp, no, so and then you have the stone. So this would be the stone, and then this would be 30 degrees, no. So Okay, so the stone, no, is carried up a ramp. Okay, so the height of the, okay, so the weight, no, of stone is 40 pounds. So this height here is 100 feet, okay, as given. So we are asked to calculate for the work done, no? So no friction is given. So the formula, obviously, for work is equal to force multiplied by the distance, okay? So, but how are we going to calculate for the force, no? So take note, force in the formula refers to the applied force, okay? So which is in parallel with the distance traversed, no? So meaning to say we'll have to break this down into components like this one, okay? So that is Wx and then Wy. W is of course the weight, no, X component and Y component. So if we try to look at, okay, so if we put an imaginary line here, so this would be 30 degrees, okay, and then this would be, of course, 60 degrees, okay. And if we try to look at, we can have this triangle, no, so that is Wx and then the weight. Okay, so this would be Wx, and of course, this would be Wy. Okay, and then this would be 60 degrees. Okay, so we don't say, no, we don't say that Wx is equivalent to the weight, no, cosine of 60. So Wx would be equivalent to, so Wx would be 20 pounds. Okay, so force done. So we can calculate, no, for the length of the ramp. So this would be 130 degrees. So we can calculate this distance d. Okay, so d here is just equivalent to 100 over sine of 30. Okay, so that is equivalent to 200 meters. Okay, so such that the work done in pushing, no, the stone, that is equivalent to Wx, which is 20 pounds, multiplied by the distance, which is 200 meters. No? Okay, that's 200, 200 feet. No? So that would give us 4,000. Okay, so that's um, foot-pound. So again, the very concept of, or the very concept in work calculation is the force, identification of the force, which is parallel to the given distance. Okay, so, and then we move to the next example. Okay, so this one. Okay, so in the next example, so we are given with, no, a pump lifts water from a lake to a large tank 20 meters above the lake. Okay, so how much work does the pump do as it transfers 5 cubic meter of water to the tank. Okay, so number 7, no? So number 7, that is, okay, number 7, so we have the, okay, so, okay, so this would be the pump, and of course, no? So the height is 20 meters. So we are asked to calculate for the work, no? So work that is equivalent to force multiplied by the distance, okay? So the force must be parallel with, no, a given distance, okay? So we can then calculate, no, for the force, which is the equal to the weight, no, of the uh, water. Okay, so the force, which is equal to the weight of the water. So the volume of the water being transported is 500 cubic meter. Okay, so that is, okay, 500 cubic meter of water. So force is very, or the force, no? We need to calculate for the value, no, of the force out from this one. Okay, so the force. Okay, so if you can remember uh, the specific weight, no, of water, so that is equivalent to 9810 Newton per cubic meter. Okay, so uh, if we want to obtain the force needed, no, to push the 500 cubic meter of water, so we can then say that the force needed is equivalent to 9810. Okay, so multiplied by, okay, so this is equivalent to 500 cubic meter. So we can cancel out this one, and of course you have the force that is 9810 times 500. So that's 4905 Newton. Okay. The work done, that is equivalent to 4 point, okay, so 905 mega Newton. Okay, so multiplied by the distance traveled, that is 20 meters. So weight or the work, no? So that is equivalent to, okay, so that's 98.1 times 10 to the power of 6 Newton meter. So this would be the answer, no? So to the given problem. Okay, so we will proceed, no, directly to the next topic. Okay, so the next topic would be the next topic would be about kinetic energy. Okay, then we have here the uh, common regular bodies, no? So to which the formula for the uh, angular velocity, no? And then also the mass moment of inertia, no? So we have this table, no? So for us to have a glimpse, no, on what is the value, no? So or what is the mass moment of inertia, okay, for this uh, common regular bodies, okay. So from time to time, just go over with this one, okay. And then we have item number 8, no? So in number 8, so you have there what is the total kinetic energy, no? So of a 3 kilogram ball whose diameter is 15 cm if it rolls across a surface, no? So a level surface, no? So with a speed of 2 meters per second. Okay, so you have there the ball. So it travels at a linear speed of 2 meters per second. Whereas at the same time, it's not just traveling linearly, it also rotates. Okay, so, and then, okay, so we are asked to calculate for the total kinetic energy. No? So, okay, total kinetic energy. So, we didn't say, no? So, we didn't say that the total, so kinetic energy total would be equal to kinetic energy linear plus kinetic energy due to uh, rotating, okay, bodies. No? So this would be linear and then the other one is for rotating bodies. Okay? So the total kinetic energy for this one is 1/2 mv square, whereas the other one is 1/2 I omega square. No? I stands for the moment of inertia. Okay? So the mass is 3 kilograms. No? So this would be 3 kilograms. Okay, so just make this one clear. 3 kilograms. Okay, so the total kinetic energy would be 1/2 multiplied by the mass. That's 3 kilograms multiplied by the speed. Okay, so that's 2 square, no? Plus 1/2. Then the moment of inertia, no, for circular bodies, that is, if you try to look back, no, so from the table, for circular bodies, that is this one, no? So for solid sphere and for hollow sphere, no? So that's 2/3 mr square. Okay, so Okay, so for the mass moment of inertia, no, that's 2/3. Let me check. Okay, so rotation, 2/3 mr square. No? So, and then, so this would be 1/2 times 2/3 of mr square. No? So, multiplied by omega square. No? So, uh, okay. So, the rotating kinetic energy can be can be calculated as 1/2 times 2/3. No? M would be 3. Then r square. No? So r square, that is, since the diameter is 15 cm, okay, so that's 15 cm diameter. So the radius is 7.5, no, cm. So 7.5 cm, that is um, 0.075 meters square. Okay, and you multiplied by omega square. Okay, so okay, this would be okay for omega. So that is okay. So the omega, no, omega. If you can remember from our previous discussion, okay, so the velocity, no, of the rotating body can be calculated using the formula V is equal to R omega. This one. So therefore, we can calculate omega as okay. So omega, therefore, that is V over R. So you have there omega square. So this would be for I, and then omega square is okay. That is V over R, no? Velocity, that's 2 over R, that's 0.075. Okay, so square. So this would be for uh, omega. Okay, so this is equivalent to this would be 4. Okay, so kinetic energy would be equivalent to uh, okay, so this would be 4 to 6, no? So plus 4. So that would be 10. Unit of force is in joules. Okay, so this would be the total kinetic energy that's acquired by the um, object. No? So while it is running linearly at the same time rotating. Okay, so Okay, and then we go to the term power, no? So power is the, okay, so power then is defined as the rate, no? So take note, rate uh, of doing work, okay? So basically when you say rate, so that is per unit time, okay? So the power, okay, so the power needed to pull, no? So an object of a mass. Okay, so let's say the mass is m, and then the height is denoted by h. So the power to pull an object, no? So with a given mass to a vertical distance h, so that's given by mgh, mass, multiplied by gravity, multiplied by height, divided by the time. Okay? And also the power needed to move an object, no? So to a distance s with a speed v. Okay, so again, no? So this is the power needed to move an object, no? So over a distance s with a speed v. Okay, so using an external force F, so power can be calculated as this one, no? The product of the force multiplied by the velocity. Okay, so these are the units, no, of power. So you have their joules per second or watts, ergs per second, pound foot per second. No? So that's the units for power. And then we have here the conversion factors. No? So to convert one unit to the other. Okay, so you have the watts to ergs, horsepower to watts, and horsepower to pound foot per second. Okay. So by the way, watts just an okay an information. No? So uh, okay, watts basically is Newton meter per second. Okay. So in English unit, so you have their pound foot per second. Okay. So we'll try to go to, okay. So we'll try to go over with problems number 9 and 10. Okay. So for item number 9, so we have here, okay. So by the use of a pulley, so a man raises a load of 50 kilograms to a height of 15 meters in 65 seconds. So find the average power. Okay. So this is power, no, of or power needed, no, to pull an object. So by means of the pulley, so the power needed to pull the object, no, so to a given or to specified height. So that is okay. So we have here item number 9. So power, that is mass, gravity, height divided by time. Take note, it's basically potential energy, no? So divided by the unit time. Okay. So the power, no, can be calculated as, okay, so that's uh, 50 kilograms. Okay, so that's gravity, that's 9.81. So the height is 15 meters divided by, of course, the time. Uh, okay, so that's 65 seconds. Okay, so that's 65 seconds. So power, that is, you have the kilograms times meter per second square times meter, okay, divided by time. So you have this one, so this will constitute to Newton multiplied by meter divided by the unit time. Newton meter per second, or basically joule per second. Okay, so how are we going to approach this one? No? So that's okay. So that would be 50 times 9.81 times 15, so divided by 65. So this would be 113.2. Okay, so that be in watts. Basically, that is joule per second. Okay, so you have the power needed. Okay, so we now go to the next sample problem. So that is for number 10, no? So, okay, so we're given here, no, how many cubic meters of water can be pumped, no? So to a height of 40 meters in 1 hour by a 5 kilowatts pump. Okay, so the question is how many cubic meters, no? So can be pumped to a height of 40 meters if the motor has, no, a power capacity of 5 kilowatts, no, assuming the efficiency is 85%. Okay, so okay, so go to the okay, number 10, no? So how many cubic meters? Okay, so okay, number 10. So the given data, no, so are the following, no? So height, that's 40 meters. The time is 1 hour. And then the power capacity, no? So power of the pump is 5 kilowatts. Then efficiency of the pump is 85%. Okay. So from this, we can calculate, no? So the input power of the pump, so that is power output divided by the efficiency, no? So which means that the output power is, okay, so 5,000 watts divided by 0.85. So we have there 882.4. Okay, unit in watts. Okay, so we now calculate no for the cubic meter needed. Okay, so basically you have the tank. So you have the pump. Okay, so the water, no, so it's height, no, from the pump, that's 40 meters, and then the force needed. Okay, so the force needed by the pump to push the water, that is equivalent to push the weight, no, of the water, that is um, force, no, so that is equivalent to the weight of the water, no. Okay, so that's okay. So to calculate for the weight, no, so we then use the formula. So the power needed, that is equivalent to force multiplied by uh, the velocity. Okay, or basically we can um, okay, so we can rewrite this one as force multiplied by force the distance. So velocity is distance per unit time, no? So that is the distance. This would be the height. Okay, so that is 40 meters divided by the time 1 hour. So that's 3,600 seconds. Okay, so P then is equal to this one. So that's 5882.4. So this should be the power, no, of the pump. So that is equivalent to force 40 divided by 3,600. Okay. So calculating for the force. So we have there so that's 529.416 Newton. Okay, so oops, the question, by the way, no, in problem number 10 is how many cubic meters. Okay, so we then, okay, so we just need to, okay, so we'll just erase this one. So the volume, okay, so the weight that is equivalent to force, no? So that's 529.416 Newton. And the specific weight, no, of the pump is, or the water. Okay, so the specific weight of water is uh, water, so that is equivalent to 9810 Newton per cubic meter. So to calculate for the volume, so volume that is equivalent to, okay, so weight divided by specific weight, no? So that is 529416 Newton divided by 9810 Newton per cubic meter. So we can calculate for the volume, that is, okay. So volume would be around 54 cubic meter. Okay, so this would be the answer. Now, so just go over with the calculations. So it would be, or it is possible now that we commit an error, no? So particularly in inputting all the data, no, in the calculator. Just go over with it, and then if there are any wrong entries, no? So all you need to do is just to replace them with the one that came out in your calculators or calculator. Okay. And okay, so okay, in example number 11, so you have there an automobile, no? So weighing 2,500 pounds, so climbs 10% grade, no, at a uniform rate of 15 miles per hour. So if the resistance is 20 pounds per ton, what horsepower is the car developing? Okay, so okay, so that's number 11. Okay. So in item number 11, so we are given with an automobile, no, so weighing 2,500 uh, pounds. So okay, so that is okay. So the okay, so the weight of the automobile is 2,500 pounds, and it climbs at 10% grade, no? So the velocity of which is 15 miles per hour, and then the inclination, no, of the plane, no, with respect to the horizontal is given by the 10% grade, no? So such that we could say tangent theta is equal to 10% or 0.1. So theta can be calculated as 5.71 degrees. Okay, so and then the resistance, no, as given, So if the resistance is 20 pound per ton, okay? So, okay, the resistance is said to be, okay, so this is the resisting force. So that is 20 pound per ton. No? So F would be 20 pound per ton. Okay. And then another thing. So, okay. And then we have here the components, no, of the weight. So the Y component and the X component, no? Because the problem is asking for what horsepower is the, okay. So the component of the weight is equivalent to, no? So we just, okay. So this should be theta. Okay, so such that this would be 90 minus theta here. Okay, so we have the following triangle. So this would be WY, WX, and 2,500, and then 90 minus theta. Okay, so we could say that WX, no, that is 2,500 cosine of 90 minus theta. Okay, so WX would be, okay, so times cosine of 90 minus theta, which is 5.71. So this would be 248.7 unit in pounds. Okay, so the resistance, okay, or the total force that needs to be exerted by the uh, vehicle in order to move must be greater than the uh, total opposing force, no? So the total opposing force that is equivalent to, no? So or the force needed is equal to the sum of the x component of the weight. So that's 248.7 pounds plus the resistance, no? So that's 20 pounds per ton. So per ton, so we can have uh, okay. So we can have 2,500 pounds, so multiplied by in 1 ton. So that's equivalent to 2,000 pounds. So long ton, no? So by default. Okay, so we can cancel this one, we can cancel this one. So such that the remaining force, okay, so that's equivalent to plus 20 times 2,500. So that's 273.7 pounds. Okay, so power then is equal to force multiplied by velocity. So we can have P, so that's 273.7 pounds multiplied by the velocity. Okay, so there's a lot of conversion of units. No? So velocity is 15 miles per hour. Okay, so you have their 5 to 80 feet per mile. And then in 1 hour, so that's equivalent to 3,600 seconds. Okay. Okay. Power then, that is equivalent to 273.7 times 15 times 5 to 80 divided by 3,600. So that's 6,021.4 times or unit in. Okay, so not times, but unit in uh, pound foot per second. Okay, so mile will cancel out. Hour will also cancel out. So this will have a unit in pounds. So you have the pound foot per second. Okay. But since the problem is asking for the HP rating, okay, so we then use HP rating that is equivalent to uh, okay, so that's we have the conversion. So 1 HP is equal to 550. So per second. So we can have the HP rating, no? Okay, so that's 6,021.4 foot per second. Okay, so times uh, in 1 HP, that's equivalent to 550 pound foot per second. So you have the pound foot per second. So HP would be that's around 10.9 horsepower. Okay, so that's for item number okay. Item number 11, no? So and after which okay, so after which we proceed no to the next topic, no? So which is law on conservation of energy. So law of conservation of energy also states that the potential energy possessed by a given object when it is moved, no, or it is made to move. So the potential energy, no, of the object does not uh, or it does not diminish right away, okay, but it is transferred or it is changed into another form, which is of the moving energy, which is the kinetic energy. No? On the other hand, so the kinetic energy possessed, no? So by moving a particular, let us say, object, uh, it will not be, or it will not become zero when it becomes to rest, but it will be equal to the potential energy, no? So developed by that object. No? So after coming to rest. That is why we have here the statement, energy cannot be created nor destroyed, but it can be changed from one form to the other. So meaning to say we can equate the two. So potential energy that's equivalent to the kinetic energy. No? So, okay, we'll try to take a look at the given sample problems. No? So clearly number 12. Okay, so, okay, in number 12, so you have there a 40 grams bullet, no? So with a speed of 300 meters per second strikes into a ballistic pendulum of mass 5 kilograms, okay, suspended from a cord 1 meters long or 1 meter long. So compute the vertical height to which the pendulum rises, okay. So, okay, we'll just use this portion here. So initially you have the bullet, so that is traveling at, okay, so that's 300 meters per second, and then it hits, no, a pendulum. Okay, so the bullet travels and it hits the pendulum. Okay, so after the impact, so the pendulum rises because of the impact. Okay, so we'll just redraw it. So there is this bullet. So a pendulum is hung. So this would be traveling at a speed of 300 meters per second. Okay, so the bullet, no, so penetrates the pendulum, so in such a way that the pendulum rises. So this would be the height. Okay, so we are asked to calculate for the vertical height, no, so uh, to which the pendulum rises. Okay. Okay, so as you can see, no, as you can see the okay, so as you can see the bullet, no, has embedded in the pendulum. Okay, so we then say that the kinetic energy, no, so the kinetic energy possessed by the bullet while in motion, so the kinetic energy was not lost, no, so it was lost in the process, but it is converted into the equivalent potential energy, no, so which is given by the height attained by the, of course, by the uh, combination of the bullet and the pendulum. Okay, so the approach should be, so the kinetic energy, no, so the kinetic energy of the bullet, so that is equivalent to the potential energy, no, so of the bullet and the pendulum, no, so this would be the total. Okay, so we then say, no, so the okay, so okay, so okay, we'll just have to redraw also the schematic for number 12. Okay, so initially we have the bullet. Okay, so with the speed now, so 300 meters per second. So it hits the pendulum, okay, so which is hung, okay, so it's hung, using a 1 meter cord. So the pendulum was hit, okay, so such that the pendulum or the bullet, no, so was embedded, no, in the pendulum like this one. Okay, so of course the pendulum, rises uh, the given height, assuming that's h. Okay, so we can say now that the kinetic energy possessed now so by the bullet, okay, so that is equivalent to the potential energy now possessed by the combination of the bullet and the pendulum. Okay, so that would be the total potential energy. No? So that means the energy possessed by the bullet when it is moving was not lost. Okay, so but rather it is being changed into potential energy. No? So that is the potential energy of the bullet and the ballistic pendulum. Okay, so we then say that the kinetic energy, that is one half. Okay, and then the total, no? So the total potential energy, no? So that is okay. This would be the mass. Okay, so that's okay. So that's the total, no? The total. Uh, so that is one half. Okay. So this would be mgh. Okay. So the kinetic energy, no, kinetic energy of the bullet is equivalent to the potential energy, no, uh, uh, total potential energy, no, so attained by having this height h. So we can cancel m, and then okay, so we have one half multiplied by 300, so that is 9.81. Course multiplied by h. So calculating for h, that would be okay. So that is so that's 300. Okay, so I think also we uh okay, so there is something wrong, no, in our analysis, but uh perhaps we can start now since we cannot equate, no, so the kinetic energy possessed by the bullet directly to the total potential energy, because the uh, total potential energy is uh, it includes the pendulum and the bullet, no? So therefore we need to find a way wherein we can analyze, no? So uh, the potential energy possessed by the uh, bullet embedded in the pendulum, and the kinetic energy also with the bullet and the pendulum, not the bullet uh, itself, no? So that means we need to do this analysis after the bullet has embedded in the pendulum. Okay, so perhaps we can do it like this way. Okay, so the same analysis. Now, so we have the bullet. So it travels at 300 meters per second. So it hits the pendulum. Okay, so now after the pendulum is hit, no, so the bullet was embedded in the pendulum, no, so such that the pendulum rises, no, so okay, so it rises, no, so with this given height h. So we would say that the same analysis, no, so the kinetic energy possessed by the bullet and the pendulum after, no, so after the bullet has embedded in the pendulum, so the combination moves at a velocity v. Okay, so the total kinetic energy, okay, so this is after the bullet now has embedded in the pendulum, that is equal to the total potential energy possessed by the bullet and the pendulum also. Okay, so a while ago, so the analysis of having the potential or the kinetic energy possessed by the bullet, so that cannot be equated directly to the potential energy, no? So possessed by the two, because the potential energy includes the uh, pendulum, no? Whereas the kinetic energy initially in our analysis is only for the bullet. Okay, so thereby we need to analyze it uh, after the impact. Okay, so kinetic energy, that is equivalent to one half mass total multiplied by the new velocity, that is mass total, okay, equal to gravity multiplied by the height. So such that we can cancel out directly mass total. Okay, so our problem now is V. So we use the impulse momentum, no? So the impulse momentum concept, okay? So, or the concept, no, of a low, or the concept of conservation of momentum. Okay, such that we have there M1 V1 plus M2 V2, so that is equivalent to M1 plus M2, then multiplied by the velocity V. Okay, so M1, that is 40 grams. Okay, so that's 0.04 kilograms multiplied by 300 plus M2, that's 5 kilograms, but multiplied with 0, since the initial velocity of the pendulum is 0, since it is hanging, that is equivalent to 5.04 multiplied by V. No? So we can calculate for V as it's 2.38, okay, meters per second. So we can have 1 half multiplied by 2.38. Okay, so that is 9.81 multiplied by H. H then is equivalent to a height of 0.289 meters. Okay, so this should be the height, no, for a given. Okay, and then uh, okay, so this should be the height, and then we proceed, no, to number 13. Okay, so in problem number 13, so you have there a boy throws a 150-gram stone, so from the top of a 20 meters cliff. So with a speed of 15 meters per second, so find its speed when it lands the river below. So for number 13, so basically you have there the cliff. Okay, so the height is 20 meters. So stone is dropped. So with an initial speed of 15 meters per second, and we are asked also to calculate the velocity also upon hitting the river. Okay, so we then say no, that the potential energy possessed by the stone. Okay, so or we would say the uh, change, no? So change in potential energy now of the stone, because there is a change in elevation. So that is change in potential energy of the stone. That is equivalent to the change in kinetic energy of the stone. So why is it that there is a change in kinetic energy? So initially, the stone is thrown at a speed of 15 meters per second, and then upon hitting the river, so the velocity changes. No? So we would say potential energy final minus potential energy initial, that is equivalent to kinetic energy final minus kinetic energy initial. Okay, so the final potential energy, so this would be 0. Okay, so because the height with respect to the uh, river is 0, so this would be minus mg, and then the height is 20 meters. So that is kinetic energy final, so that is 1/2 mass of the stone velocity square minus kinetic energy, no, initial kinetic energy, that is 1/2 mass of the stone multiplied by the velocity, initial velocity square. No? So such that we can cancel m. Okay, so we can then calculate, no, So 9.81 multiplied by 20, that is equivalent to 1/2 of v square minus 1/2 of 15 square. Okay, so that is 9.81. Okay, so we have negative, no? So that's 9.81 times 20. Okay, okay, uh, okay, so we'll just write again, no? So the uh, solution, no, for item number 13. Okay, so we would say, no, that so there is this ball or stone, no, so which is thrown by the boy at a height of 20 meters, so it hits the river below. So this would be the river. So the initial velocity of the stone is 15 meters per second, and the stone hits the river at a given velocity v. Okay, so we'll revise our analysis a while ago. No? So uh, we didn't say that the uh, potential energy, no, possessed by the stone. Okay, so that's the potential energy possessed by the stone. So that is equal to the change in kinetic energy, no? So uh, possessed by the stone while it is moving, no? Okay. So why is it that there is change, no? So there is a change in kinetic energy because initially the stone is dropped, no? So or thrown at a given speed, and then uh, the speed, no? So when it hits the river is of course different, okay? So than the initial speed. So we would say, no, that the potential energy possessed by the stone initially is mass of the stone multiplied by the gravitational pull multiplied by the height h. So the kinetic energy possessed by the change in, no? So that's equivalent to this one. No? So that's v square minus initial velocity square. Okay, so we can cancel out m. Okay, so such that we have 2 times 9.81 times 20, that is equivalent to v square minus 15 square. Okay, so such that v square or v, no, we can just calculate directly v. That is 2 times 9.81 times 20, no? So plus 15 square. So then you took the square up, no? So then that would be 24.85 meters per second. Okay. Or we can just, okay, so that's equivalent to, okay, if you remember the rectilinear, vertical rectilinear motion, so we can make use of the formula Vf square, that is initial square, so plus 2 times gravity times the distance s, no, or height s. So we can say the final velocity, that is initial 15 square plus 2 times 9.81 multiplied by the height 20. So still you can have, okay, so that is 2 times 9.81 times 20. Still the answer is 24.85 meters per second. Okay. So this shows, no, so an alternative solution, no, so using the first discussed topic, the rectilinear motion, the vertical rectilinear motion. Okay. And then we go to the last sample problem, no, of the topic. Okay, so problem number 14. Okay. So number 14, so you have there a solid cylinder, 30 cm in diameter. So at the top of an incline or an incline, no, 2 meters high is released and rolls down the, okay, inclined without loss of energy, no, so due to friction, no, so find the angular speed at the bottom. Okay, so okay, so okay, in number 14, so we have here a solid cylinder. Okay, so it actually rolls down. So the velocity of the cylinder, okay, so let us say the velocity, no, initial velocity of the cylinder at the top is 0. Okay, so it started to roll down to a point that it reaches at the bottom. So with a velocity, a known velocity, and of course, while the cylinder moves, no, from the top to bottom, it actually also rolls down like this one, no? Okay. So the, or number 14, no? Number 14. So we are asked to, okay, so this would be the height, no? Initially, the height is 2 meters. Okay. So we are asked with the angular velocity, no? Omega at the bottom, no? Okay. First is we have to establish the relationship, no, between V and omega. From our previous discussion, V is equal to R multiplied by omega. And also the inertia of a solid cylinder is 0 0.5 or 1/2 mr squared. Okay. So we begin, no, our analysis, no, so that the potential energy, no, so the potential energy possessed by the cylinder at the top, so that is equal to the change in kinetic energy, no, of the cylinder. Okay, so uh, which is equivalent to Ke final minus Ke initial, so which happens to be 0. Okay, so because initially the cylinder is at rest. Okay, so we then say that we have mgh. So the kinetic energy, no, so that is 1/2 mv square. No, so for the linear kinetic energy at the same time, since it is rolling, so that's plus 1/2. Okay, so I omega square. Okay, so we can further write this one as mgh. That's 1/2 uh, m. V is equal to r omega square plus 1/2. Okay, I is equal to 1/2 m r square. Okay, multiplied by omega. No, so this would be omega square. Okay, so let's try to find out which variable can be cancelled out. So we can cancel out m at the same time m. Okay, and then we multiply it with 2. Okay, so that we can have it as 2 times 9.81. So multiplied by the height, that is 2. That is r square. No? So radius is 0.15. Okay, so multiplied by omega square plus, okay, so we still have 0.5 here. And then 0.15, no? This for r square times omega square. Okay, so we can have 2 times 9.81 times 2, okay, divided by 0.15 square plus 0.5 times 0.15 square. Okay, so omega then can be calculated as, okay, so you have there 34.1. Okay, so you have there 34.1. No? So, okay, for the answer. Okay, so